Hello, everyone, and welcome back to another programming demo for cybersecurity fundamentals. In this video, we are going to be looking at the implementation of the digital signature verification scheme using the public key infrastructure and the specific algorithm for RSA. And this will be implemented in Python. Okay. So going over the security logic for digital signature verification schemes using RSA. The first thing that we have to know, and we have already discussed this when we talked about the chapter for cryptographic tools and the various concepts that are involved in that chapter. So to do a quick revision on the topic that we are going to be implementing, the first thing that we have to know is what is a digital signature, right? So a digital signature is basically the output of a cryptographic transformation on data, and that data could be a file or a message or any other form of data block, right? And when we properly implement that mechanism for digital signature verification, that allows us to verify the origin, that is the sender of the message, to authenticate if the person who is sending the message and claiming the identity of that sender, we can verify if that person is the person who is sending us the message. It also allows us to authenticate the integrity of the data that is being transmitted. So that means if you download a data from, let's say, any kind of platform, then how do you verify that the data has not been tampered with? So that is something that can be implemented or ensured using digital signatures. And then finally, digital signature also provides us with a mechanism to implement the security concept of non-repudiation, such that in a situation where, let's say, if you take certain action or if you provide some kind of file, and then later on, if there is a security issue or a vulnerability of repudiation, what can happen in such a situation is that somebody can share a file with you or somebody can take a certain action. And then later on, if there is no accountability, then they can simply say that they did not do that particular action, right? So that is basically the security vulnerability of repudiation. So what digital signatures enable is the process of non-repudiation, such that if somebody takes a certain action within a particular network, then because a signature is associated to that action, they will not be able to not say that they didn't do that action in a future instance, right? So that enables the process of non-repudiation, right? So the digital signature itself is a data-dependent bit pattern, okay? And then it is generated as a function of the input file or the message or any other form of data block that we just mentioned right now. So what you can do with it, that is, once the digital signatures are generated, you can get that data block and the digital signature that is associated with that data block and verify that that particular data or message has been signed by the alleged signer or whoever the sender is. And we can also verify that the data block is not altered after the signing has taken place and that the signer cannot repudiate the signature, which basically is the benefits of digital signature that we spoke of or that we discussed in this particular slide, right? There are three different algorithms that are available in order to implement digital signature. So we have the first one, which is called the digital signature algorithm or DSA, okay? And then we have the RSA algorithm, okay, which is based on the RSA public key algorithm. And then we have the elliptic curve digital signature algorithm, or better known in the acronym of ECDSA, which is based on the elliptic curve cryptography, right? So we discussed all these three things in details during our class lectures. So the one that I'm going to be using for the mock implementation of the digital signature verification scheme is basically the RSA public key algorithm. So to give an overview of what the digital signature implementation process involves from a cybersecurity standpoint, is there are two phases to it. The first phase is known as the signature creation, and then the second phase is called the verification of the signature verify process, right? So in the first step, what happens is that we would have some sort of a message. And again, this message could be a file, it could be a block of data, something along those lines, right? And then we pass it through a cryptographic hash function. So for example, this cryptographic hash function could be in the form of SHA-2, which could be SHA-256 or SHA-512. So once that is sent through the hash function, it creates a more summarized digest of the original message, reduces it in size, brings it to a fixed length, which is cryptographic in nature. And then, given that we are using the RSA public key algorithm, we have a public key and a private key pair for every sender and receiver, but the receiver is not of concern in this particular implementation. So we take the private key of the sender, and then we sign the hash that has been generated by the hash function in order, and then pass it through the digital signature generation algorithm, which in our case would be using the RSA algorithm, and that will generate the signature. Then we take the message, we append the signature to the message, and this is what gets transmitted over the network. So once that message and the appended signature is received by the receiver, okay, then what is done is that the receiver takes the signature, again passes it as an input to the digital signature verification algorithm, but this time to kind of decrypt it in a way. So in a manner of speaking, they access the public key of the sender. So since it is a public key, so that means it is publicly available, like we discussed, and that will generate the, well, not that will generate, but that is one of the inputs. And then we can take the message and again pass it through the same hash function. So if we have used, or if the sender used SHA-256 here or SHA-512, then they will also use the same hash function here, pass the message through the hash function, which will generate the hash code. And that will also be sent as the third input to the digital signature verification algorithm. And given that this particular message has not been tampered with after it has been signed, then it will return the verification whether the signature is valid or not. So a few things to keep in mind here, that the first aspect, which is the block has been signed by the alleged signer, is basically supported by the idea that if the block has not been signed by the alleged signer, then you cannot, this particular input to the digital signature verification algorithm, when you're trying to verify the signature, will essentially fail, right? So because there is an inverse aspect of the public key and private key pair, right? So that means if you encrypt using the private key, then you can decrypt using the public key. Or if you encrypt using the public key, then the corresponding private key pair of that particular public key can only decrypt that particular encrypted message, right? So that essentially ensures that you can, verify that the data block has been signed by the alleged sender, okay? And with no alteration, assuming that this message, when it was transmitted by the sender, was tampered with, okay, during the process of transmission, and once it was received, then if you pass it through the hash function, then the hash that will be generated during the verification step will be different from the hash that was probably generated before the transmission by the sender. So essentially, if that is the case, then this signature will be invalid. And essentially, you would be able to figure out that the message has been altered after the message was signed and transmitted to you, right? So those are the two basic ways, or those are the structure of the scheme that we are using that enables the guarantees of these 2 points that we have discussed here, right? So overall, what we see is that if we have a plain text input, right, and if the sender takes their private key, encrypts it, passes it through the digital signature verification scheme, of course, we need a hash function here. The overview does not include the hash part here, but within this box, the hash operations are also included, like it is shown here in this particular step. And then we transmit that. And once it is received, again, within this box, the receiver is going to take the public key of the public-private key pair of the sender and then pass it through the process of verification, which again involves the hash function, and that will generate the plain text output, right? So this is basically the cybersecurity overview of the digital signature verification scheme. From the programming perspective, when we want to implement this, there is a prerequisite that we have to first address, just like we had some prerequisites of some external libraries, some dependencies of our program when we were doing the implementation of the password storage, right, and the digital authentication verification scheme. So in this particular case, we will need a library that is named cryptography. So before we can start our program, we have to make sure that we install this external dependency, this library, by using the command pip install, and then the name of the library is cryptography itself. We also would need to create a mock or test file. Okay, so remember this plain text input or this message that will be signed and transmitted and then later on verified. We have to create a mock file for that. So what we are going to be doing is in our root directory where we will implement this program, we will create a test file.txt and we will put like a very simple hello world type of a message there, which will act as our input to the scheme here, right? And then after those two things, we would implement the program in three different functions. Okay, we will break down the overall logic or the steps that needs to be implemented within three functions. Okay, the first function will be responsible for generating the public and private keys of the sender. So here you can see that there is a private key here for the sender, and then there is a public key here for the sender, right? So we first need to generate that particular private and public key pair for the sender, which can then be used by the sender to sign their message before they want to transmit it. And the public key pair can be used by the simulated receiver in order to verify the digital signature, essentially, right? Then we will have another function which will be responsible for performing the first phase of the scheme's implementation, which is to sign the message itself. So here that will be implemented using a function. And then the second phase, which is to basically verify the signature, we will write the logic of that implementation within another function that is responsible for that particular step, right? So essentially, we will have the code broken down into three different functions: one to generate the public-private key pair, one to sign or to create the digital signature and then sign the mock file that we have created in the prerequisite step, and then another function that implements the verification stage of the digital signature scheme, right? In terms of the programming constructs that will be used in this program, we would have our typical functions that we have seen in the last two programming demos. We will have the file input output operations as well, because here we will have to take a file. We would have a file that will be able to store the private key and a file that will be able to store the public key. And then the signature itself will be stored as a file, which can eventually be appended to a message in a realistic setting if you're transmitting that, right? So we would have file input output operations so that we can write to those different files and then we can read from those different files in order to perform our verifications. Okay. And other than that, everything else, every other cryptographic transformation operations that will be implemented, we will be taking the aid of our external dependency library, the cryptography library that we have installed, and various inbuilt functions that comes with that particular library. And we will see that when we go in a few moments and start implementing those libraries. So those are basically coming from the library itself, right? Various different functions, like generating the large prime numbers, generating the cryptographic keys using modular arithmetic and stuff like that, right? So that will be done. We won't be writing that from scratch manually, but we will be using some of the inbuilt functions that are available through the cryptography library itself, okay? So we have discussed these programming constructs in the previous programs. If you would like to see the tutorial on how file input output works, then I will suggest that you watch the previous video in this series, which is basically the implementation of a password storage and digital authentication verification scheme. Functions we have discussed in the last two programs as well, so you can check any one of those particular videos to revise your concept on how functions are implemented in Python, essentially. Okay, so with that, we will switch over to our Visual Studio Code editor and move forward with the implementation of this particular program. Okay, so here we are in my Visual Studio Code editor. If you notice, what I have already done here is I have created a subfolder in my parent folder, and this is something that will be available in the GitHub repository, all the code that I'm going to write here. I have created a Python script here, and I have named it RSA digital signature verification.py. And I have also created a mock file here, and I have named it testfile.txt. You can name it whatever you want. And I have written like a very simple message here that this is a test file to check the digital signature verification scheme that will be implemented using the RSA algorithm, right? So we will put that down, and that will be acting as our prerequisite, essentially, okay? So after this, please remember that before you start the implementation, you will have to execute this command called pip install cryptography. So I have already installed this in my own computer, in my local system. So these are the three different files that will essentially, or three different associated libraries that will be installed as a part of installing the cryptography library. So when you run this, then essentially all these three files will be installed. And you can check the versions here. These are the versions that I am using, right? So you will probably be getting the same versions as well. And then you need to make sure that you run this command first before you start writing any of the codes, okay? So to go ahead and write down what do we need first is we will first do the same process that we did. That is, we will break down the program and write down the three different functions that we will be using in order to implement the overall logic of the code, right? So as we discussed, those three functions are going to be first for generating the public and private keys and storing them in some file, okay, so that it can later be referred to. The second will be to sign the message. So this will be let us call it phase one of digital signature verification scheme. Okay, and then the third phase or the third step would be to verify the signed message. Okay, so we can call this as phase two of the digital signature verification scheme. All right, and then we will write a step 0 here, and we will say import the necessary functions or import the necessary dependencies required to implement the following. All right, and the following is basically to perform these three operations essentially. Okay, so here we will create some sections. So we will say import statements, and then we will have main logic of the program, and we can write the I won't say the demo, but essentially the outline of the three functions that will be implementing these three particular steps, right? So following the syntax for Python, we will define three functions, give it a name, and leave the body empty. And then step by step, we will address each of these bodies as we go over the logic. So let's say we define a function to generate our keys. So we can call it generate underscore keys. Okay, and the first brackets indicate that this is a function. This will not require any type of input. So the values of the input parameter here within the first brackets is going to be empty, followed by a colon. And then we are just going to write a pass as a placeholder statement so that we don't get any errors. And then we will come back to this when we actually start writing the logic. Okay, so let us do the same thing for the other two functions that we will need. So we will need another function, which will be responsible for signing the message or signing the file, right? So here we have a file. So we'll just say def sign file, okay? And then when we are signing the file, we have to provide as a input what that file is, okay? So what we will do is we will write a variable name here, and we will just simply call it file name. And this file name essentially will have the name of this file, which will be passed as an input here, okay? So we will take that input when we run the main function somewhere, or we will predefine it and we will provide it as a predefined input. But however, if you want to, try out your comfort, if you're new to learning Python, right, then what you can do is instead of predefining the input, you will see later on what I mean by predefining an input, where we just, statically set the file name within the program itself. So instead of doing that static file name, what you can do is you can modify that part of the code that I'm going to provide you, and you can do an input-output exchange with the user, like I showed you in the previous program when we were doing the password storage and digital authentication, such that in this particular input-output scenario, you can give some, basically you can ask the user to provide the file name, and they will provide the name of the file, and then you will take that as an input from the user and then assign that to the variable, which will essentially be passed as an input parameter to this sign file and verify file function, right? So here we will just leave it as a pass again. And then we will move on to the last file that will be present here, which will be responsible for verifying the signature. And we will call it verify_signature. Okay. Hopefully I have no typos here. And again, this will require an input of file name. So we will provide a variable, which we are labeling as file name for the time being, in order to verify the signature. And we will just put a pass statement here just to avoid any kind of errors for the time being. Okay. So then we will move on to step 0, which is the import statements. So the first thing that we need to import is basically the RSA crypto functions. Okay. I said that there will be some inbuilt functions that we will be using in order to implement various concepts, such as generating the mathematics that is required to generate the public key and the private key, the operations on large primes, modular arithmetic, and all those type of stuff. We will also need some padding. Okay, remember we talked about padding during the hashing topics of our cybersecurity fundamentals, where we said that instead of generating variable length keys, which can be susceptible to reverse engineering attacks, and to figure out, if you have some clues, you can figure out essentially which keys was used to generate which cryptographic primitives and those kind of stuff. So what you do is that using padding, you always generate this fixed length outputs, which makes it more difficult to reverse engineering attacks or cryptanalysis attacks, essentially, right? So we will need the cryptographic functions here, which will help us generate the public key, private key. We will also need some padding schemes in order to make sure that we can generate fixed size secure message encoding. So these padding schemes will be for secure message encoding, essentially. Okay? That's so that it makes it more difficult to do any kind of cryptanalysis attacks here, right? So to do that, what we do is we use the from keyword. So this is the syntax in Python, followed by the library that we are going to be using. So the library that we have is basically the cryptography library. So within this cryptographic library, we need to get to a specific set. So remember, the cryptographic library, cryptography can be divided into symmetric algorithms and asymmetric algorithms and stuff like that, right? So here, since our choice of algorithm is basically RSA, which is a part of the asymmetric library, and the padding, that scheme that we are going to be using, is also a part of that. Okay, so we need to get to the point where we can get the asymmetric libraries, right? So this is present inside this particular file hierarchy structure. So in Hazmat, we need to go to primitives, and then inside primitives, we can take this asymmetric part, this one. So you can see here we have ciphers here, we have hashes, we have secure hashes, HMAC and CMAC, right? So there are many different primitives here. So we need this padding guide, and we need the asymmetric one once we get it. Okay. So from this asymmetric file, so this is basically a file hierarchy. So you can think of this like a folder, and then there is a subfolder inside that. There is another subfolder, and that from there we need a file, right? So if I had to, let's say, grab this particular file, this RSA digital signature verification.py, I had to import that somewhere. And if my library was cybersecurity_fundamentals, so I would have something along the lines of from cybersecurity fundamentals dot digital signature verification import RSA digital signature verification, right? So that is what I'm doing here, is that I'm writing the file hierarchy within this particular module. And then from this file hierarchy, I need two things. So I'm going to use the keyword called import, and then I will specify the files that I specifically need, which is RSA and then padding. Okay, so I need these two guys here. Okay. The other next step, so these are all for the cryptographic operations for generating the keys. The next thing that I will need essentially is hashing functions. As we just discussed in the preliminaries and the conceptual overview, we need to hash the message in order to reduce the digest, so that we don't have a very large file that we are signing using RSA, and that will be computationally intensive, right? So here we will need hashing algorithms. And the hashing algorithms that I will use in this particular implementation example is basically the SHA-256, right? So what this will enable us is to hash the message before signing it. Okay. And again, we have to do the same thing. So we will do the cryptography module. Within that, we have hazmat. And then inside of this, we have primitives. And then within that primitives, we have a file that is called hashes, right? And within this is where we can grab the SHA-256 function from there, okay? We also need to store the keys and the input-output keys that we are going to be generating, right? The public-private key in byte formats, right? We don't want to store it in the numerical value. We want to convert it into binary representation and then store those binary representations in the file, right? So for that, we again need another library. So this is basically to convert the keys, the secure keys, either to or from byte formats for storage purposes. Okay, so this is basically to store the encryption keys, right? So again, we will go to from cryptography. Again, we have to go inside hazmat. And then inside hazmat, we will have to go inside primitives. Okay. And then within primitives, we will be importing the library that we call serialization. Okay. And this will enable the conversion to and from byte formats. Okay. And then finally, instead of doing all these operations manually, the operations of generating the keys, generating the hashes, performing the serialization, etc., we need a secure way of implementing it rather than choosing to implement it manually, right? So we want to specify what we technically call as a backend provider for these cryptographic functions, like who is going to be performing these cryptographic operations. So within this library, again, there is a file that is called default backend. So we would explicitly specify that file in order to tell the program that this is where the implementation is being supported from. And we are not implementing any of these operations that is listed in any of these particular files manually, right? So here, basically what we're saying, specify who will securely implement these functions or these processes that are involved, the cryptographic processes that are essentially involved, right? So for that, we again will go to our cryptography library. Within cryptography library, we will follow the same hierarchy structure that is inside hazmat. But now instead of going to primitives, we are going to be going to backends, okay? And then we are going to be importing the default backend that is available with this. So even if we do not specify this, then it will still use the default backend, right? But just for, as a sanity check, we are explicitly specifying that just to make sure that the program uses the inbuilt functionalities to implement all of these different processes, rather than expecting us to manually implement them by using the function calls within these particular files, right? So that takes care of uh, the import statements that we need in order to implement this. So then we can move on to our next step, which is to generate the keys. Now, I have already discussed the logic behind the generation of keys for RSA. We have done like a mock solving of the mathematics that are involved. So if you have any doubts there, you can check those out. But essentially, we need a very large prime exponent, and we need to have a key size specified. And then that will be used to essentially generate the private key. And then using the private key, we will essentially use that to generate the public key using the inbuilt function. So the first thing that I'm going to do here is create a variable that will store the private key. So we'll call it private key. Then we will use the RSA method that we have imported into our program in line 10. You can see that RSA has now been highlighted, and you can see the rest of the files that we have imported, like padding, hashes, serialization. These are not yet highlighted because we have not yet used the functionalities from these imports, right? But the moment I write RSA here, it gets highlighted here as well, okay? So using RSA, inside that particular file, we can see that there is a method that is present within that file, okay, which is called generate private key. And generate private key is a function or a method, right? And that has three different types of input parameters. The first one is the public exponent. So the public exponent that we are going to be using, and this is based on the concept of large prime values. So we have a large prime values that we are required to use in order to securely generate the public key and the private key pair. Again, please check out the videos on the solution of the mathematical aspect of RSA to kind of revise and get a better understanding of what we are going to be doing here. So the public exponent that we are going to be using in this particular case will be a large prime number value, and the value that we choose, which is selected by default in many different applications, which provides a good balance between security and the computational power that is required in order to implement that, okay? Because these things, the computation can get very intense in a few steps, okay? So the value that we are going to be choosing, the prime number value, is 2 to the power 16 plus 1, which gives us an output of around 65537, okay? So this is kind of like a default value, not a default value, but this is kind of like a well-balanced value. So for example, if I choose a value of 13 or 17, this will be a pretty small number, right? So remember, in class, we use these two values, or I believe 11 or 13, something along those lines, as our starting point, right? So this doesn't provide sufficient security, okay? And if you would like to, you can choose a prime number value which is bigger than this number, and the amount of security that you get in comparison to those bigger numbers, when you compare it to this, is not significantly large, right? You just, at that point of time, after you pass this particular values limit, you just end up, making your computation more difficult, right? More intensive. It requires more resources. It requires more time to implement. So that is not worth it because you're not getting any added value in terms of the security. So you don't want to choose a number that is too small. You don't want to choose a number that is way too big. I mean, you can choose it. So we want a kind of like a balance between security and performance, okay? So this is the value that people generally choose in order to achieve that particular balance, okay? In addition to this, we also need to specify the key size that we are using for our RSA algorithm. So the default key size right now, not this big, 2048 bits. Okay. So this is the default key size or the well-balanced key size that is currently used for RSA, given the current hardware and software improvements that we see. And then we also need to specify the backend as to who will be implementing these operations. Okay. So remember, we imported this default backend. So essentially, we will be specifying here that in order to perform this operation, we will be using the default backend such that these operations of generating the private key is done by the library and not manually by us. Okay. So we will go ahead and start writing the first input parameter. So the first input parameter is the public exponent, which is going to be a large prime number, which is 65537. Okay. Thereafter, we need the key size. So key size, we are just going to say 2048. And then we need the backend. So for the backend, we are just going to say we will use the default backend, and this is a method. So we will essentially put this here. Okay. So that is essentially all that we need for the private key generation, and this will take care of it. So the next thing that we need to do once the private key has been generated, we need to generate the corresponding public key. So we'll create a variable that will store this public key, and then we will use the private key variable, which will essentially store the private key, and then to it, we will call the public key generation function, which is again present in the cryptographic library, the RSA cryptographic library. Remember, the private key is an instance of the RSA. So as a result of that, we can also access the public key part, which is also present in RSA. We don't have to do RSA.public key here because this is basically an instantiation of RSA itself. So as a result of that, if I use the variable, which, well, it's not a variable at this point, but if I use this, then I can access the methods and the properties that is associated with that particular object, right? So that essentially will generate the public key and the private key. So once the generation has been done, we need to save this in a particular file. Because remember, in a more practical scenario, you will keep the private key private. So you will save it in some secure fashion on your local systems that cannot be accessed over the network. So nobody can come and steal it. And then the public key will essentially remain public. So that means you can post it to some kind of a web forum. You can send it over an email and stuff like that. So generally, the nature of the public key is essentially public, right? So we want to save this in files so that it can be referred to for later operations, right? So here, essentially what we need to do is basically we need to perform some sort of a file input output to save the public and private key pair. Okay, so again, in order to perform file input output using Python, we will use the with keyword and the open function. And then inside of this, we will specify the name of the file, which will store our private key and public key. So we will start with the private key first. So we will call the file private_key, and we will store it as a PEM file. Okay, so the .pem extension is used in order to store the public keys and the private keys essentially. And then we will open this file in write mode for binary. Okay, so this is basically everything is binary key here that will be stored in this particular .pem file. So we are opening the file in write mode for binary operations. Okay, and now we will create an instantiation of this file writer. So we'll write as f, and then we will go inside this particular method. And then here we will say f.write. Okay, and what we want to write here is basically the private key variable, which is private_key that we have here. Okay, and we need to first convert this into byte format and then store it in the PEM file, right? So for that, we will access another inbuilt function, which we call private_bytes, which is a part of RSA again. Okay, and then inside private_bytes, we will open, this is a method. We need to provide three different inputs. First is what is the encoding format? So the encoding format, remember we had imported this library in order to convert keys to and from byte formats. So we are going to grab this guy here now, and we're going to put serialization. And within serialization, there is a method called encoding. So we will grab that method. And the encoding has to be in PEM format. So you can see here there are many different encodings for different types of file type. So we have already declared it as .pem. So we are going to be grabbing that. So once we grab that, then we have to specify the format. So we will go ahead and do the formatting. So again, we need the serialization dot, and this is basically for private key. So we are saying private format. So this will change to public format when we do the same thing for public key. Okay. And this will follow the standards of traditional open SSL security libraries. Okay. And then finally, we have to specify the encryption algorithm. Now, since we are performing data signature, this is not about confidentiality and this is not about key exchange. So our goal is not to encrypt the keys at all. So here we will not be specifying any encryption algorithms to encrypt the keys and then store it. So what we will do is we will call serialization and then we will simply say no encryption. So this will be stored as essentially plain text. Okay. So that will basically be the overall output for this particular file, okay, or this particular storage. So that will take care of our storage here. All right. So once this is done, then the next thing that we need, so this is the end of this particular write operation. So now we need to save the public key in a file. Right? So we'll do the same operations, but we will make some changes that is relevant to the public key. So starting with open, change the file name first. So we will say public key and again .pem format. Okay. And then this needs to be opened in write mode for bytes. Okay. And we will create the instantiation of the file writer and then f.write. Okay. And then what do we want to put inside f.write? The same thing. We will first grab the public key variable. All right. We will convert that to public bytes, not private. Okay. This is a method. We then have to specify the encoding. All right. So the encoding is from the serialization inside encoding with a capital E, and then the encoding has to be for PEM formats. So that is the first input parameter. And the second input parameter will be essentially formatting. So again, we will grab serialization. Instead of saying private format, here we will say public format. And then what we need to add after that is the subject public key information, which is basically the standardization, or not the standard, but how you essentially store public keys, right? So there is no encryption here, like you saw here, okay? And then the format is basically like the one that I have implemented here on line 30, okay? So that takes care of our implementation for the generation of keys. Now we can move to the next function, which is to sign the file. Okay, so to sign the file, we need two things inside of this. Of course, the first thing, we need the file itself. So we need to perform a file read operation on this particular file here. And then wherever this files are going to be, these files for private key, we need that. Okay, because we are signing it, we need to sign using the private key and the file, and then we need to perform hashing on that. So the first thing that we are going to be doing is we need to grab our private key. Okay, so we need to read the file which stores the private key. So again, with open, we need to provide the name of the file, and the name of the file has to be exactly the one that we provided here. So I'm just going to copy this. All right. And then I'm going to open this file in read mode for bytes. Okay, so here I will say RB. I will create an instantiation of the file reader. Okay, so then we can do private key. So we'll create another variable here. And remember, even though the name of this variable is the same as this variable, however, since these are declared inside of different function bodies, we cannot use this particular variable inside of this particular function. So even though the name are the same, their scope is different. So by scope, it means where can you use that particular declaration, right? So this private key can be used only inside this particular function, and this private key can only be used inside this particular function, okay? So that is why we can still use the same name, because the scope of this is essentially different, okay? So we need to call serialization again, because we need to convert the encoding that we had done here back to something that is readable by the program and we can process in the program itself. So we will say load, and then we need the PEM private key. So where is PEM private key? PEM private key here. Okay, so this is for the private key itself. Input f dot read. So you have to read the file. Okay. Is there a password that we have provided to read this file? There is none. And then we have to specify our backend, which will be essentially our default backend function. Okay, so that takes care of the storage of the private key back into our program. So next thing is we need to read our main file itself that we intend to cite. So we will do with open, and then the file name is essentially stored inside this variable called file name, which is local to sign file. So we will open this file in RB mode again, create an instantiation, F, and then here we will just create another variable, let's call it file data, and then the file data will store whatever the file read instance is grabbing, okay? And once this is done, we have the inputs that is necessary to perform our main operation within this particular function, which is to sign the file using RSA plus probabilistic padding. So we will use the PSS padding. This is basically known as the probabilistic signature scheme. And then in addition to that, we also would be using the SHA-256 hashing algorithm. Okay, so PSS is basically probabilistic signature scheme. It is one of the secure signature schemes that is used to create a fixed length output for RSA algorithms. Okay, and then for SHA-256, we'll be using what we call as the MGF, or the mask generation function version 1, in order, which is a part of SHA-256, in order to implement the hashing. In addition to this, we also need a salt. Remember salt from our password generation. So the salt kind of adds more security. And we want to increase the length of the generated signature to the maximum length possible using the salt, okay? So we will first create a variable here, and we will call it signature. The signature will take the private key that we have within this function on line 34, and then it has an associated method to it, which we call as simply sign. So the sign will take inputs of the file data, the padding, and when we perform the padding, we will carry out the hashing and then append to the hashing the salt value that is required, okay? And then we will call SHA-256 to finally perform the hashing, which will complete the signing operation. So let us go ahead and do that. So our file is stored inside the variable file data, all the content that is read, all right? And once that is taken care of, the next thing is we want to add some padding to it. So for that, we'll be using the padding, and we will be using the probabilistic signature scheme for the padding itself. So this is basically a function, and we have to provide two inputs to it. First, we will specify what the masking function is going to be. So the masking function will be padding dot, and the masking that we will use is basically MGF, which is masking generation function 1, version 1. Okay. And then this calls on hashes that we have imported earlier. And within hashes, we have SHA-256. So we will do SHA, here we go, SHA-256. All right, so this is the method. So we have to put the brackets here. So once this is taken care of, then what we need is to add the salt. So we will say the salt length is going to be equals to padding dot PSS dot, and then we will use the max length of the salt value that is available. Okay, and then we have to specify the hashing function that we are using here. So for the hashing function, we will call hashes and then dot SHA-256. Where is it? Here. Right. So that will take care of the hashing itself. So that is basically the overall implementation of the signature. So once that is done, the next step here, we are still not done. We have to save the signature so that can be transmitted during a practical setup. So save the generated signature in line 40. Hopefully it will remain line 40 for you guys as well when you open it. So, okay, we don't need this. So here, what we are going to do is we need to create a file output operation again and store the signature in binary format. So we will do with open. So let us open this, and we have to name the file which will store the signature. So let us call it signature, and the extension for signature files, we use .sig for that. Okay, and then we need to open this file in write mode for bytes as f, and then here we are simply just going to do f.write, and then inside of this we will put our signature, and that is stored inside this guy here. So we will place it in, and just for sanity's purposes, once this is done, before we exit the function, we are simply going to write a print statement, a prompt that will give a verification that, let's say, file has been signed successfully. Okay, something along these lines, 3 dots, and that takes care of the signature part, right? Next, we have the verification of the signature. So the first thing we need as input here, just like we did when we started off, where is the function? Here. So we needed the private key, we needed the file. So what we need here is basically the public key. We need the file as well as the signature. Okay, remember when we discussed the conceptual overview for the verification stage, we need 3 inputs: the public key, the signature, and the original message itself. All right, so we need to start getting that into our program when we work here. So the first thing that we want to do is with open, and we need to open our public key. So we need to go back, find where we saved our public key. So this was our public key. So we need to come back here, put it here, but we need to open this in read mode for bytes. Okay, and then we will essentially store this information by changing the encoding back inside a variable. So we will say the variable's name is public key, and again this variable is different from the public key variable in the generation of the key function. We will use serialization in order to convert it back. So we will do load underscore pem, but this time we need it for public key. So where is public key? Here, public key. Okay, so this is going to be a function, and the first input is going to be f.read, and the second input is going to be backend default. All right, so that takes care of the generation of, not generation, but converting the public key from the file and store it in the program for operation purposes. All right, next thing is we need the original file itself, which we want to verify. So we will say with open, and then we need to provide the file name. So the actual file name will be stored inside this variable, and we need to open it in read byte mode. and as F. And then what we want to do inside of that is create a variable, and we will call it file data. And we will store inside of that F dot read. All right. And then we need another input. So we will do with open. And now we need to finally grab the third and last input, which is the signature. So we will grab this, paste it here, and we will open this in read byte modes again. Okay. So as F, and let me see, what do we have? So we need to store this in a variable. So we will do signature is equals to F dot read. Okay, simply just read it and store it inside the variable. All right. So after this, the next thing that we want to do is verify the signature. Okay, so that is basically the step after this. So in order to verify the signature, we are going to wrap it inside what we call as the try except block or the try catch block. So what it does, it first tries to perform a certain operation. So here, the certain operation is the verification of the signature. Okay. And if the signature verification is successful, that is, if the try part of the program implementation is successful, then it will give the particular prompt. Otherwise, it will give the print statement, which will say that the verification failed, right? So this is another way in which we can make sure that we only first check if the verification is right. And if the verification is right, then only we give the prompt. Otherwise, we do not perform any kind of prompt outputs that might say otherwise, okay? So this is implemented using the try. Okay, so first we are going to set up this try block. So it's like another way of implementing the if-else statement for an oversimplified explanation of what is happening here. So what happens here is first the verification will be tried. So we are going to take the public key. Then we are going to call on the verify function, not the sign function this time, but the verify function. And the verify function will have an input of the signature itself. All right. The next thing is the original file that we are using. And then we again have to perform the same padding operations, masking operation, and salt length, and then hashing using SHA-256 for that file data, right? So we have to write the same things. So we will call upon padding. We'll call upon the probabilistic scheme, okay? And then inside of that, we will have two inputs, just like we did. So what is the masking function? The masking function is coming from padding dot mgf1, and that uses hashes dot SHA-256, and this is a method. All right. So after this, we will have the next input. Let me just double check. I have not made any mistakes with the brackets anywhere. All right. Looks about right, hopefully. We need to give a salt length. So the salt underscore length, length, is going to be equals to padding dot pss dot max length. Okay, so the max length of the salt that will be provided. And then finally, we have the input of, so I think I have made a mistake somewhere, because this should not leave outside the verify bracket. There should be another input that we did. Let me just double check what I had here. Yeah, it should look something like this. Right, so hashes dot SHA-256, it will be the last input here. So I've got to paste this here. So yeah, we got the error. So that means this bracket has to finish, I believe, here. Okay, so that takes care of the input for the verification. And now if the verification is done, it is going to print some sort of a prompt message. And we can say that signature is valid, something along these lines, any kind of message that you can think of that will give you. Now, since we have a try block, we need to give an except. All right. So in the except block, we are going to write the invalid prompt. So here we will say signature is not valid, something else. Okay. So that will take care of the try catch block. Okay. And then finally, in order to set this function up for execution, we need to declare a main function. So we are going to do if underscore underscore name of the file underscore underscore is equals main underscore underscore main underscore underscore. These are all syntax. Okay. Then that is, if I am running this program, then this will be treated as the main function itself. Then the functions that I need to execute in order is basically the generate keys functions that I have written, which has no input. Then I will call the second function. What is the name of the second function? Sign file. Okay, so here sign file will have an input. So this is where I'm going to provide my input. Now, you can change this. This is what I meant by static input, because I am predefining the input here to test file .txt, and this is present inside my root directory. So this is what I'm specifying here. What you can do is you can change this process to practice a little bit of programming, where you can request the input of this from the user and then store it in a variable and then pass that variable as an input to this particular function. Okay. And then the other thing that you can do is, not the other thing, but the next step will be to verify the signature. So I believe this is the name of the file. Yeah. And then we will provide as input the file that we are verifying, which in our case is test file only. So few things that you can do in order to practice is change this process, get input from the user rather than predefining it. You can also change this process to get the input from the user rather than predefining it. The other thing that you can do is, in order to test that this actually works, right? Instead of calling this in serial fashion like we have here, what you can do is you can comment this out, right? Run this first, get the signature and everything, and then change the content of the file that we have here. Anything that you change, any message that you add, any singular letter change, and then run this verify and see whether or not you get this particular prompt. Okay, so let us go ahead and check if we have done this program correctly, at least for its whatever we have implemented. So let me see where I am. Okay, so I am in the correct folder. So I'm now going to run this program. So I'm going to say Python RSA digital verification signature. So when I'm calling this program by its name, essentially this will be treated as the main function, and then it will execute all these three functions in order. Okay, so let's see if we get any errors here. Okay, so no errors. Everything has been generated real quick. And now if you pay attention to the new contents in our file, we first have a private key.pem file. So you can see here, this 2048-bit private key was generated. We have the public key, right? So this will be public. So this can be read by the public. And then finally, we have the signature, which is in binary format. So I do not have an extension which can essentially read a .sig file. So you are seeing all these weird characters here. But if you have any kind of extensions to read a .sig file, or you can use the internet, then essentially the signature can be read in a way that makes sense, right? So that is basically the implementation. What is more complicated here, or what basically is the learning curve, essentially, is not just the programming logic of what is implemented, but to understand the relevant inbuilt functions that is necessary to implement the different stages, right? When we discuss the logic, we do not consider certain things. Like, for example, when we are hashing it, and we just discussed it from the point of view of the digital signature, we did not discuss the fact that, padding is required, masking is required. We have to add a salt in order to make it practically more secure, rather than from a theoretical standpoint where we are just discussing the overview and how the signature scheme works, right? We don't discuss all of that. But when you want to implement it, you would want to make sure that you include all the steps that is involved in making sure that everything is secure or securely generated, right? So these are some of the things that you have to understand. And from a beginner standpoint, it would be better to just, keep a track of the methods that were called from these libraries that we imported, and have a note or an explanation of what they are, why you are using it in this particular implementation. Okay, so that's it. And I'll keep you posted on the next programming implementations after this, which I think we are going to start. Not we're going to start, but I think we will go ahead and implement how to write access control permissions and policies, and we will try to design the access permissions for a mock firewall and implement that using Python. All right. So that's it, and have a great day ahead.